first introductions for some of our theorems that are in this chapter. So, unlike yesterday where we were just kind of going through and reminding ourselves of some math, today we're actually starting to add to that postulate sheet. So if you're filling out the postulate sheet and your notes packet simultaneously, make sure you grab that out as well. If you're not and you're filling it out later, that's fine. So, the two theorems that we're going to be talking about today are both fairly easy theorems. One of them you've seen before. The other one is just a really super easy one. And that's the first one, is the super easy one, the triangle inequality theorem that says the sum of any two lengths of a triangle has to add up to be bigger than the third side length. So if I have a triangle, and I'm just going to say for the short version of it, if, and then triangle ABC. And then we're going to draw a picture that kind of helps us out with this triangle. Then. Now before we get to actually filling in the then of this theorem, we got to talk about something that in talking about right triangles and trigonometry, we got to talk about a change in notation. In geometry, generally speaking, when we talk about segments, for example, this segment right here, what is the name of this bottom segment? CB or BC, and the true name of it has the bar above it. When we get into working with right triangles and trigonometry, we take a step away from that notation for side lengths of triangles. Instead, when it comes to talking about angles and side lengths and triangles, we start by just using single letters, provided, of course, we don't have that situation where multiple angles can be called angle A. The corners, the vertices, the angles, if you will be called capital letters, and the side lengths are the same exact letters but lowercase. So, those of y'all who have been writing BC as a side length as lowercase letters, no, for multiple reasons. Those of you who switch out your capital and your lowercase letters as you're writing, you need to move away from that. You need to be picky about capital versus lowercase letters. Because capital letters are angles or corners of triangles and lowercase letters are sides. And the way that it works is if this is a capital A, the side across from that side in the triangle, or from that angle. This angle's up here, the side across is this one. We call it a lowercase a. The angle and the side opposite have the same letter. One is capital, one is lowercase. Which means this one right here, the one we typically would have called AC, what letter should it be? B, because it's the angle that's not touching. This one right here is lowercase c. Now, we needed that to talk about this theorem. Now, going back to this theorem says that if I add up any two side lengths, that number better be bigger than the third side length. So A plus B in lowercase better be bigger than the lowercase c. To go along with that, B plus C, again both lowercase, better be bigger than A. And A plus C better be bigger than B. If all three of those inequalities do not hold true in a list of side lengths for a triangle, then that triangle cannot exist. It comes from the fact that if I have those lengths, if I have those set lengths, I have to be able to close the triangle in. If the side lengths are too small, they kind of work like a T-Rex where it can't clap its hands. They don't reach if the side lengths are too small. If the side lengths add up to be equal, where 2 add up to be equal to the third, then it collapses in on itself to create a line. So it has to have, every combination of 2 sides has to be bigger than the side that wasn't counted. Now, this leads us to the questions. Yes, Colin?
I was just going to see if you knew why T-Rexes can't touch their elbows together or touch their hands in general.
Little arms?
No, it's because they're dead.
Oh.
Okay, back to math. Now, this theorem is used to determine if it's possible for a triangle to be created with certain side lengths. Now, when it comes right down to it, the only time we're going to have issues is in situations where you're talking about the small side and the medium side adding up to get bigger than the large side. So while all 3 of these inequalities must hold, if you check the small plus the medium to see if that is bigger than the large, that will be enough to see if the triangle is possible. So, determine whether it is possible for a triangle to have the following side lengths. Show your reasoning. Okay, step 1. Determine which one's the large side. Between 4, 8, and 9, which one's the large one? 9. Yes, that is pretty easy. Okay, that's the large one. Add the 2 small ones together. And you are going to try to see how they relate to the large one. I'm just putting a big open box there for me to put something into it. What is 4 plus 8? 12. So I got 12. I got 9. Is 12 bigger than 9?
Yes.
12 is indeed greater than 9, which means there is a triangle possible. Ta-da. That answered the question. Now, it does say show your reasoning, which means this right here, you have to write. If you don't write this step, if you don't circle your 9, that's fine. But at minimum on questions like this, I need to see 12 is greater than 9, the triangle is possible. Okay, problem B. Which one's the biggest? 18. So which ones am I adding together? 8 plus 9, I'm checking out its relationship with 18. What is 8 plus 9? 17. Checking out its relationship with 18. 17 compared to 18. Smaller. We are on page 5 of our notes. If 17 is smaller than 18, if these 2 added together is smaller, that means, correct, no triangle possible. Triangle is not possible. Again, you don't have to write out all 3 of these steps, but which ones do you need? Which of these 3 lines do you need to write down for me to give you points on problems like this? The middle one and the bottom one. The bottom one's the answer, the middle one's the show your reasoning. Okay. Problem C, 5, 7, and 12. What do I do? Twelve is bigger, so add the 7 and the 5. 7 and 5. 12. What is 12's relationship with 12? It is equal. Does my theorem have equal signs in it? No, which means? This is still no triangle possible. I said the first theorem was really easy. Do you agree with me? Okay. Add up the 2, make sure it's bigger than the third. If it's bigger than the third, the triangle is possible. If it is smaller than or exactly the same as the third, it's no triangle possible. Now, the other theorem that you're going to see today requires knowing a little bit of vocabulary about right triangles. Particularly the longest side of a right triangle and the two other sides. The longest side of a right triangle, which by the way is always across from the right angle, is known as the hypotenuse. Does that sound like a familiar word? You would have talked about it in middle school. The other two sides are called legs. So that's a leg and that's a leg. Now, knowing about the hypotenuse and legs leads us to the Pythagorean theorem, which you would have talked about in middle school. So if I have triangle ABC, and if triangle ABC is a right triangle, with C, the right angle, then my triangle looks like this. It is triangle ABC, which means its sides are A, B, and C. This one down here, is it A, B, or C? That's A because it's not touching angle A, so lowercase a. What about this one over here? B because it's not touching angle B. And this one? C, lowercase c. Okay, if I have a right triangle in which side lengths are A, B, and C, specifically the idea is that C is the hypotenuse. Then A squared plus B squared equals C squared. Sound familiar? One of the first things that's actually called a theorem when it's taught to you. You've worked with many theorems way before geometry. You just didn't necessarily know they were called theorems. This one typically holds its name of being a theorem. And you learn it in like 7th grade, I think is the first time-ish. And if it doesn't look familiar, that's okay. We're going through it again. Once you get this down, go ahead and flip the page. I'm just waiting until people get it written down. A squared plus B squared equals C squared is a relationship between the side lengths of a right triangle. It allows us to solve for missing side lengths in a right triangle specifically. Has to be a right triangle. If it is not a right triangle, this does not apply. Is that a right triangle? Yeah. How do you know it's a right triangle? It's got a right angle. It's got a little box in the corner. Okay, so we can use A squared plus B squared equals C squared. First thing you got to do, identify the hypotenuse. Which side's the longest side? X. Now you could tell it's the longest side by looking at it. How else could you have told that that was the hypotenuse? Where is it in relation to the right angle?
Right across.
Always across from it. Okay, which means in the A squared plus B squared equals C squared, that's going to go into the C location. Between A and B, I don't care which leg goes in which. You just got to put the numbers in. I'm going to start with the 5. 5 squared plus 12 squared equals X squared. The 5 and the 12. Again, it doesn't matter which order you put them in for A and B. The pickiness about Pythagorean theorem is hypotenuse must go into C. And now we solve our equation. How do you think I should start solving this equation? I cannot add the 5 and the 12. I have to find the square of them first. Because adding the 5 and the 12 is a simplify step. When you're doing simplify, you're doing PEMDAS, and the exponent needs to come before the adding and subtracting. Once we start doing the opposite operations, moving things from one side to the other, then we do PEMDAS backwards. Okay, 5 squared is 25. 12 squared is 144, equal to x squared. Now we can add them together. 25 plus 144 is 169. 169 is equal to x squared. Get rid of the squared. Take the square root. Now when you take a square root, what should you typically put with it? Plus minus. But we are solving for the side length of a triangle. Does the negative have any application here? No. So you don't need the plus or minus. The positive and negative version, I only need the positive version. What is the square root of 169? 13. Good. Problem B. Is it a right triangle? Beautiful. Which side's the hypotenuse? The 13. So that goes in the C location in a squared plus b squared equals c squared. Does it matter which of the other two sides goes in A and which one goes in B? No. Do you want to start with the x or the 11? Sure. You just got to make a choice at that point. X squared plus 11 squared equals 13. Shockingly enough, squared. What do we do next? Square things. What's 11 squared? You got calculators for a reason, and if you don't have a calculator, you should grab one. It is 121. 13 squared. $169. Now what? Minus the 121 this time. The numbers are not on the same side of the equal sign, so we're doing opposite operations. X squared equals 48. Get rid of squared, we take the square root. Do we need the plus or minus? No, why? It's the side length of a triangle. Side lengths of the triangle cannot be negative. Rounding to the nearest hundredth. What is the square root of 48? 6 point what? Indeed. Okay. Going to my name cards. I'm hearing a lot from the same people. Problem C. Isabel. Where do I need to start in this process? X is the C. You have to determine which side is that hypotenuse and recognize that that has to be C. Beautiful. Aiden, what comes next? What will that look like? I just heard squared the second time. What got squared?
4.
Beautiful. Equals? Exactly. Do not forget the squares. It's the most common thing that I see people do is they just accidentally forget to put a square on something. Dom, what should I do now? Start squaring things. What is 6 squared? What about 4 squared? Ooh. 16. Do not lose your squared on your x. Again, a very common mistake. People lose the squared. Nate, now what?
Square root.
Ooh, not yet.
Wait, no. You add them first.
What do we get?
Yeah, 52.
Vivian, now what? What do we get? 7 point. Sorry, I missed the decimal. Good. I'm deaf sometimes. Beautiful. Okay, I'm gonna do one more with name cards, and then we're gonna talk about ones that look a little bit different. Probably going through some name cards with them, but I gotta talk about it. Okay, problem D. Elena, where do I start? Recognize which side's the hypotenuse, call it C. Trayton. What comes next? Beautiful. Kylie. Now what? Square both of them. Connor, what is 7.9 squared? Ooh, not square root, squared.
Oh.
Nope. What's with the laptop?
I'm waiting for you to be done so I can make tabs.
It's the bathroom, go ahead.
Okay.
62.41, you got it. BG, what is 10.6 squared? Lily. Now what? You got it. X squared is 49.95. Cam, how do I finish it off? Square root. That thingamajob. What do we get, Cam? 7 point. Ooh, we're rounding to 2 decimal places. 0.07, but yeah. Okay. The last 2 problems probably look a little bit scary to some of y'all. But here's the thing. The last 2 problems, even though they involve ugly numbers, you do the exact same thing. Brody,
Yeah.
which side's going to be my hypotenuse on question E?
Square root 122.
Yep. And then we plug into our Pythagorean theorem the same way we were. I'm going to start with the x squared and then go to the 10 squared and equal to the square root of 122 squared. Now when it's just a single square root with nothing in front of it, what do squares and square roots do? Cancel each other out. Now you can type in the square root of 122 and then square it, and it'll just tell you it's 122. 10 squared is 100, by the way. Haley, do I add or subtract at this point? Yep. X squared equals 22. Charlie, how do I finish a problem like this? Do I need the plus or minus? No. And square root of 22 is 4.69. So when it's a single square root like that, you just do the same stuff. Now there's a slight complication when you've got a side that looks like this. So there's going to be a tiny difference on this last problem on what you do. But before we get to dealing with that, Colin, where do we start on the problem?
We find C.
Which one?
Square root of 13.
Yep, that's my hypotenuse, that's C. Okay, we write our equation. Greta, what's the equation going to look like?
2
Square root 3.
square root of 3, and then plus x squared equals square root of 13.
Don't forget the squared on the first one. And when it is 2 square roots of 3 like that, when it's got that multiple piece square root and plain number going on, it needs to go in parentheses. Now, squaring that, even though it should be fairly straightforward because it should be something you type into your calculator, squaring that becomes one of the biggest issues that people have because of how it types into the calculator. Now, when squaring something like that, because there is no plus or minus in it, in all technicality, it's like squaring the 2 and squaring the square root of 3 and then multiplying them together. What is 2 squared? 4. Square root of 3 squared, square and square root would cancel, and so you'd be left with 3. So in all technicality, it should be 4 times 3, which is 12. We should get 12. But if you don't type it into your calculator correctly, you're not going to get 12. Here's the most common way I see people type it in. Even if they know this parenthesis has to go there. They do an open parenthesis, they do 2, they do square root of 3, they close the parenthesis, and then they square it, and the calculator tells them the answer is 6. Do you see the problem? How many open parentheses are there? Look again, not 1, 2. Which means you need to close both sets of parentheses before you square it. Anyone that uses a TI calculator is going to have this problem, unless you have a TI-84. And when I'm talking about TI-84, I mean the fancier TI-84, not even the old TI-84s. Those graphing calculators, the TI-83s, So you have to make sure, because your TI calculator opens a parenthesis here every time it puts a square root, so you have to close and close before you square it. So be careful with that. Beyond that, the rest of this problem works the exact same way. Square root of 13 squared is 13. I'm just going to go through it quickly. We subtract the 12, we get 1, and then we take the square root. And the square root of 1 just happens to be 1. But you have to be careful with those. So if you have a TI calculator, or you typically use a TI calculator, you might want to write yourself a note to remind yourself to close all parentheses and then square it. Okay. How are we feeling about today's stuff? Today's stuff is typically pretty straightforward. 9.1, day 1. Today's the 26th. Our homework is due on Friday. Friday is the 28th. 9.1, worksheet 1.